So now we will work on in-class exercise to chapter 4, problem F4.14. Determine the magnitude of the moment of the force F about the axis OA. So this is different than the previous in-class exercise where we were calculating moment about a point. Now we are calculating moment about an axis. So for that, if we use triple scalar product, so axis OA is non-standard axis. It's not either X, Y, or Z. So we need to determine the unit vector along the axis of interest, which is OA. So we will find out that by first determining the position vector between OA and dividing the position vector by magnitude to get the unit vector. Then second, we need position vector between the axis of rotation and the force vector. So we will calculate that by setting the A as the tail of the vector and B as the head of the vector. And that will be our R, position vector for moment. The first position vector is for axis, second position vector is for moment, and F is already given. So then we can use triple scalar product to get the answer. So let's look at this problem. So we need coordinates of point O, A, and B because those are the points of interest. So coordinates of point O are 0, 0, 0. Coordinates of point A are 0.3, 0.4, 0. Coordinates of point B are 0.3, 0.4, and minus 0.2. So this is positive x, this is positive y, and this is positive z, and b is in the direction of negative z, below xy plane, so it has negative 0.2, this point to here. And the final answer, moment of this force about axis OA, can be calculated using unit vector for that axis dot product r AB or OB. We can select ROB for this matter, cross F. See, we can have two different position vectors for the moment calculation. We can have AB as one of the position vector, or we can also select OB as our position vector. And there is advantage of selecting OB as our position vector because the O coordinates of O are 0, 0, 0. So that will simplify our calculation a little bit. So let's take the steps. So this is our final equation, equation number 1. So for that, we need each one of these components individually. We have been given the value of f directly as a Cartesian vector. And the f for this problem is 300i minus 200j plus 150k. Okay, so this is given 300 minus 200, 150 newtons. Now let's calculate ROB. So you can calculate based on the coordinates of O and B. So it's coordinates of B minus coordinates of O. And ROB is 0.3i plus 0.4j minus 0.2k. And this is in meters. Now for UOA, we need to first calculate ROA and divide by that ROA by its magnitude and to get the unit vector. So ROA is coordinates of A minus coordinates of O, that is 0.3i plus 0.4j plus 0k. Because A is in xy plane, so it doesn't have any z coordinates, and that's meters. But then we find out the unit vector UOA by dividing ROA with the magnitude of ROA. And magnitude of ROA is calculated using square root of 0.3 square plus 0.4 square. Yeah, so when we do that, we get UOA as 0.6i plus 0.8j plus 0k. And this does not have any unit because this is unitless. Once again, our OA is calculated as square root of zero point 0.3 square plus 0.4 square plus 0 square. So this is 0.5. So basically you divide each component by 0.5. So 0.3 divided by 0.5, 0.4 divided by 0.5, and 0 divided by 0.5. Now it's time to substitute F, R, OB, and UOA into this equation. And that equation is actually for a 3 cross 3 matrix. So we can write that as MOA is equal to UOA dot R cross F, which is three coordinates of U. So 0.6, 0.8, and 0. So there's three numbers. Middle row is for R, 0.3, 0.4, minus 0.2, and third one is for F, 300, minus 200, 150. And now you solve the matrix determinant. So it's same as before, but now we don't have ijk, we have all 9 numbers. So it's 0.6, and in the bracket it's 0.4 multiplied by 150 minus 0.2 minus 0.2 multiplied by minus 200, and so on. So let's do it here. 0.6 in bracket it's 0.4 multiplied by 150 minus 0.2 multiplied by minus 200. That's the first part. Then negative sign. Then the second element of the first row, 0.8, it's 0.3 multiplied by 150 minus 0.2 multiplied by 300. And third, plus 0. Bracket doesn't matter because 0 multiplied by anything is 0. So the final answer we get is minus 72 Newton meter. That means the moment is about clockwise rotation, clockwise direction. Yeah, so that's our final answer. So let's look at the approach. So we needed unit vector along the axis of rotation OA. So that we determine based on the position vector here. Then we need position vector between R and F. Between the position vector R between the axis and the point of rotation. So we have selected O and B as our 2 points. It can be AB as well. So if you take point A and B for this R, if you take RAB, you will still get the same answer. You can try this yourself if you like. And F is given as Cartesian vector, then we have used triple scalar product and calculated the final moment using matrix determinant. Thank you.